Good day and welcome back for part 1 of our next major topic, triple integrals. In this video we will attempt to define the basic idea of a triple integral, get a little bit of intuition in terms of what it might calculate for us, and see an example. Thinking back to double integrals, we started off with the most ideal scenario possible. That is to say, we integrated over a rectangle. For a triple integral, we are going to be integrating over a solid object, and what we are going to integrate over first is a three-dimensional rectangle, which I will oftentimes just refer to as being a box. So this would be a three-dimensional rectangle. And the question is, how should we evaluate the integral over such a box? And if we use the intuition we have from double integrals and integrating over rectangles, we should simply add in our limits of integration. But the first and maybe big decision we need to make is when we integrate over this box, we have an x, y, and z variables to worry about. Hence this triple integral. And the decision we need to make is, how should we order our variables of integration? As there are three different variables to include, there's several different ways to do it. And note, we start off with three possibilities inside, then two in the middle, and just one variable left over on the outside. So how many possible orders are there for our integration? And if you said 6, I agree. So note, over a box, one of these three-dimensional rectangles, you can use any of the 6 possible orders of integration. Similar to a double integral, in something we previously had called Fubini's theorem, you could use either order of integration that you preferred depending upon the function you were integrating. And the same idea holds true here. Depending upon f and which variable would be more convenient to place on the inside, you can order those limits of integration or the variables of integration however you prefer. And just to demonstrate here, I'll go ahead and write dx, dy, dz, and then we put into place our corresponding limits of integration. X from a to b, y from c to d, z from r to s, where we're thinking all of those 6 quantities are representing constants. So a to b on the inside, y is in the middle from c to d, and z is on the outside from r to s. And let me give you kind of a quick reminder and hopefully a bit of intuition as to how we can interpret this triple integral. So recall, a property of interest related to double integrals is if we integrate over a region D and the function we are integrating is simply 1, what we get back is the area of D. And note, there is a triple integral analog of this. If we are evaluating the triple integral over some solid, and we integrate the function 1, note notationally the dv is referring in a sense to a small piece of volume, and E is a solid. What we would get back is the volume of the solid E. Let me also make another observation kind of relating this back to interpretations of the double integral. Recall that we interpreted the double integral as giving us something about a net difference of enclosed volumes. The same idea is going to be true here. It's just not something we can really visualize and probably don't have good intuition for. A triple integral in general will tell us something about a net difference in hypervolumes, which would be four-dimensional version of volumes. So a net difference of hypervolumes. And this isn't something I'm going to spend any time discussing because it's not something we can easily visualize nor do we typically have any intuition related to hypervolumes. But let me note there's also this interpretation that we can pick up from double integrals, is that you can use a triple integral to find the mass of some solid if you have its density function. So we do have some motivation as to why something like this would be of interest and why we would want to be able to calculate it. With that in mind, let's just dive into an example. Let's evaluate the triple integral of the function xz minus y cubed over the box B defined above, where the x values go from -1 to 1, the y values from 0 to 2, the z values from 0 to 1. Now, the first choice that we have to make in a sense here is how do we want to order our variables of integration? And it turns out we can, as mentioned above, use any order that we prefer. And I do not see any strong reason why I would want to choose one over another to get started. So I'm going to go ahead and just use an arbitrary dx, dy, dz, but you could certainly evaluate these in any order you prefer, and if done correctly, you will come up with the same answer. So on the inside we have x from -1 to 1, in the middle we have y from 0 to 2, and on the outside we have z from 0 to 1. And similar to double integrals, when we are evaluating these iterated integrals, we work our way from the inside out. So we start off with that inside antiderivative with respect to x. And note, when we are integrating with respect to x, the z and the y cubed are constants. So integrating with respect to x, we have 1/2 x squared z minus xy cubed, and we're evaluating this from x equals -1 to x equals 1. And similar to our earlier discussion, I always recommend writing specifically which variable you are substituting into, because now that there are 3 variables, it's even easier to make kind of a silly mistake that we wouldn't want to. So we replace each x with a 1, and then minus sign, replace it with a -1. So when we replace x with 1, we have 1/2 z minus y cubed minus 1/2 z, now it's plus y cubed. And the reason it's plus is we have minus a -1. And then we are left over with dy dz. And note this works out quite well in a sense. You have positive 1/2 z minus 1/2 z because this minus sign distributes. Then you have a minus y cubed minus y cubed. So we can simplify the function we are integrating down to -2y cubed. And note, once we've gotten it down to this point, that is to say we've started off with the inside integral and we've evaluated it, this is an old familiar problem. So at this point, we've now just turned this simply into a double integral. So this is familiar. And note, as far as double integrals go, this is as good as it gets. We are integrating over a rectangle, and the function we're integrating is a function of y times a function of z. And in this case, there's a times 1 hiding that can play the role of the function of z. So we can break it up into 2 single integrals. The integral with respect to z multiplied by this integral with respect to y. The value of the first integral is simply 1. The value of the second integral, if we integrate, we would have minus 2/4 y to the 4th, evaluated from 2 to 0. So we substitute in 2, we put a minus sign, we substitute in 0. So that would be minus 1/2 2 to the 4th minus, well, the 0 we get when we substitute in 0. 2 to the 4th is 16, multiplied by minus 1/2 gives us back minus 8. And no, minus 8 is the solution or the value of this triple integral, but it's not something I'm going to attempt to try to visualize or interpret as some type of hypervolume. So this completes our introduction into triple integrals, where we have integrated over a three-dimensional rectangle or a box. The next question we want to ask, much like we did with double integrals, is what if our solid of integration now is not one of these boxes? What's going to be the analog here of our type 1 and type 2 regions that we have previously encountered? So stay tuned and take care.